We can write that, right? And then sum over i's.
Yeah.
So now we have our this expression, and we know like we have our expression for pi as well. So we can actually substitute this thing inside of that D'Alembert's principle. So let's write this: ai dot delta ri, and obviously summed over I, equals to ddt vi dot delta ri summed over I minus sum over I vi dot delta ri dot. So what is ri dot? What is ri dot? What is this thing? Hello? What is ri dot?
Is the I component of the velocity.
No, it's the velocity on the ith particle.
Oh, sorry, velocity of the ith particle.
Yeah, so this is basically vi, right? Okay, so and what else do we have? We have the part that we need to substitute and see what it does. So
There is a mi, I guess.
oh, am I missing this thing?
Yeah.
Okay, now it's fine.
I don't think del ri dot should be the velocity, because del ri dot is arbitrary. It's not the direction in which the particle is actually traveling.
Sorry?
I don't understand why del ri dot is the velocity.
No. Ri dot is the velocity.
Oh, it's not del ri dot.
No, the del is there.
No, but when we say del ri dot, don't we mean an arbitrary direction in which the particle is not traveling?
No, delta ri dot is that.
Yeah.
But delta ri is that. But ri dot is rate of change of r with respect to time.
Oh, yeah, right. Yeah, right.
So do not confuse with like time derivative and variational derivative. Those are two things.
But here we have delta ri. Here we have delta ri.
Here we have
Delta ri, and we are taking the derivative of delta ri.
Okay. I get it. I get it. So you're saying that ddt of delta ri, how come this thing is basically variation of v, right?
I mean, it should be some form of velocity, but I don't think it is the velocity of the particle. In the sense that the particle is really going in that direction.
No. Okay. So when you talk about say like infinitesimal displacement dr on a two-dimensional plane, say, still this thing is arbitrary, right? This dr can be in any direction, any arbitrary direction. But what your dr by dt is, this is actually velocity. That particle actually has taken that direction.
Yes.
So these are two things. dr, it's arbitrary, that's not a problem. But dr over dt, we mean by that is how much that particle has traveled in a particular time.
Okay. So in that sense, is del vi and ai does those two have the same direction? Does del vi and AI have the same direction? And AI?
I don't see it. Why?
I mean, del vi is the variation in velocity, and acceleration is the rate of change of velocity. So
No. If you take derivative of that, ddt of that,
yeah.
then you get variation of AI. But variation of VI is not proportional to AI.
Yeah, it's not proper. Do they have the same direction though?
They are not proportional. That means they do not have the same direction as well. That's why I wrote those are not proportional. So for velocity being proportional is like they have same direction, right?
Yeah.
Like two vectors, if those two vectors are proportional, then they have same direction as well.
Yeah. Okay.
Okay, we'll see like what this variational derivative means. We'll see in a moment. Just hold on to it a little bit.
Yeah. Okay.
Or if you are like not comfortable with taking that notation, actually I should do it in a like more rigorous way. That I can do it as well. That I can do. So here we had like ddt of variation of Ri, right? This is we had actually. So you're not comfortable taking dot on Ri. So that's also okay.
I'm
So I can.
comfortable with the notation. I was just concerned about whether that means the.
Okay. Yeah, I understand. It's not just about notation. It's about like you're confused about. Okay, those are different things. Then how come like taking the derivative of that thing becomes the velocity? Okay, we'll see that later. Then just now take like substitute that thing and do not say that this thing is velocity, variation of velocity. I think that you can agree, right? So sum over m, and then okay, now ddt of something. This of something we write it explicitly. So what is vi in terms of our dots? Sum over j delta ri over delta qj dot plus delta ri by delta t. This whole thing, this whole thing dot with variation of ri. And what is variation of ri? This is nothing but delta ri by delta qj. Obviously they have sum over j, variation qj. You can write like that. Hello.
Yeah.
Okay. And we have the next term. We have sum over I, mi, and then vi. Again, explicitly write down the vi, sum over j, delta ri over delta qj dot plus delta ri by delta t. This thing now again dotted with ddt of variation of r, which is delta ri by delta qj, variation of qj, sum over j. Did I use same? No, I should use k over here, otherwise it will confuse the index. I'll use k to sum over this. Yeah. So this thing. So far so good. Now we need to explicitly like take those dot products and let's see what happens. The basic target is express this ddt of something as a derivative with partial derivative with respect to qj. That's the target here. Okay. So to do that, sum over I mi ddt okay, this is gonna be a long algebra if we do this way. Do about it. Okay, let's not worry about this too much at this stage. Okay, so so take derivative or like ddt of this whole thing. So this is sum over j, sum over k, delta ri over delta qj dot delta ri over delta qk. I'm going to write that variation qk at the last, like out of the sum. So this is one part, and then delta ri by delta t dot partial derivative of ri with respect to qk, then variation qk. Okay, this is one part. We do the same thing for the other one as well. So minus sum over I mi okay. So for this part, actually, we cannot do anything. We can do much. So just write as it is. Next step, it will reduce down. So sum over j, sum over k, delta ri by delta qj dot ddt of delta ri by delta qk, variation qk. This is one thing, plus delta ri by delta t dot ddt delta ri by delta qk, variation qk. Okay, so now our main goal is, look, here we have derivative, but inside of the derivative we have like variation of qk. So we actually somehow cancel derivative of qk from here and from there as well. So we expand this part in product rule, but only like take this thing as a whole and the rest as a one part. And again, this thing, like just expand this thing in product rule, and then like separate the ddt of variation of qk. So it's gonna be a mess for a moment, but it's be simplified. So sum over j, sum over k, delta ri. Oops, I have a ddt. ddt. ddt of this thing, sum over j, sum over k, delta ri by delta qj, qj dot delta ri by delta qk. This is one part, and another is plus delta ri by delta t dot delta ri by delta qk. This is one part, ddt of this thing multiplied by variation qk. This is one part, and another is plus we are expanding this thing in product rules. So sum over I mi, sum this second bracket, let's write the second bracket as well, sum over j, sum over k, delta ri by delta qj, qj dot delta ri by delta qk, plus delta ri by delta t dot delta ri by delta qk. This thing, and then ddt of variation qk. This is one part, and another is the rest. So for the other one, let's write down the derivative of variation qk first. So if you expand this thing in product rule, so one is derivative of delta ri over delta qk, and another is derivative of variation qk. So let's write down the second term first. So it gives you sum over mi, sum over I mi, then sum over j, sum over k, delta ri by delta qj, qj dot ddt, delta ri by delta qk, if we expand this thing in product rule, so the second term, that's what we are trying to write, is this delta ri by delta qk plus delta ri by delta t dot delta ri by delta qk. This thing, and then we have the rest. Yeah. So let's put a second bracket over there. ddt of delta qk, and then we need to write the rest. So that is negative sum over I mi. Actually, I did it in the most complicated way possible, I believe. Delta qj dot delta ri by delta qk. Oh, so now instead of delta ri by delta qk, we would have derivative of that thing. So derivative of that thing, ddt of delta ri by delta qk, this thing, plus delta ri by delta t dot ddt of delta ri by delta qk, and then finally we have out of the parenthesis we have variation of qk. So yeah, so can we see that these two terms, this term and this term, cancel out? Hello?
Yeah.
So everyone agrees that those two terms cancel out? Those two terms cancel out?
Yeah.
Okay. Also, for the rest, we have taken variation of qk as the factor out, right? Like we can factor out the whole thing. So we can write like this: sum over k at the last. Like we can take this sum out of the whole, like those sums are actually switchable because j and k and I, those are all independent indices. So we can do any sum later, right? So we are summing over the k at the last. So then inside of that we have mi sum over j. Actually, we have sum over I as well. How do I write it? Okay, sum over k, sum over I, mi. Now I can write it. Okay, so ddt of sum over j, these two terms, so delta ri by delta qj dot delta ri by delta qk plus delta ri by delta t dot delta ri by delta qk. We can write like that. So there is a second parenthesis over there. Then we have a derivative of that thing. Oh, also plus the next term. Actually, the next term is minus. Actually, the last one, this one. So actually, I'm taking variation of qk as a factor at the end. So that's why it looks a little bit messy at this step. So negative. So this term I'm writing. This term. This term. So sum over I, that's I have taken, and then k. Then we have mi, and then we have started the square bracket. Then we need to write sum over j delta ri by delta qj dot ddt of delta ri by delta qk plus then we have delta ri by delta t dot ddt of delta ri by delta qk. You can write like that, okay? This term is inside of the sum and the rest. Then in the parenthesis, then write down variation of qk. Okay, so we can do that. Everyone agrees?
Yeah.
Okay, so almost we are done actually. Now it will simplify a lot. So see, we have sum over k, sum over I, mi, then ddt of something. But in that something, we have like delta ri over delta qj dot delta ri by delta qk. And again, delta ri by delta t partial derivative dot delta ri by delta qk. So we can again factor out the delta ri by delta qk, right? And write our expression like this. Sum over j delta ri by delta qj dot plus delta ri by delta t dot partial derivative now delta ri by delta qk. You can write like that. Okay, for the first term, this one.
Yeah.
Okay, And for the second term, what do we have? Okay, so for the second term, we have negative that mi is already factored out. So sum over j, we're actually trying to factor out some similar thing out of here. So the similar thing is here ddt of something, right? That thing we are going to take as a factor, like factoring out of this whole thing. So we can write it like that. So delta ri by delta qj dot plus delta ri by delta t, this is whole thing, dot ddt of delta ri by delta qk. And then we have the whole variation of qk. Is that okay?
Yeah.
So tell me, what is this thing? What is this whole thing? Like sum over j delta ri by delta qj dot plus delta ri by delta t.
VI.
Velocity.
It's the velocity.
It's
It's
vi.
actual velocity.
Yeah, this is actual velocity. But the question is, did I miss some? Did I like something? DDT something? I think so. I think I missed one thing. This DDT, right?
What?
Yeah. Where did I write that DDT? Like I just wrote this sum. That's fine. And but
Well,
this whole
above term.
huh?
The DDT was in the above term. So
No, I'm trying to write this term, right? This term over there.
yeah.
There should be a DDT.
Yeah, there should be.
Yeah.
So
Missed
this
that
is what I missed, like DDT of this whole thing. That's what I wanted to write.
Yeah. Now it's all right.
Okay. So yeah. So we have sum over k, sum over I, mi, then DDT of this whole thing. And what's the whole thing is? This is number one vi dot delta ri by delta qk. Right? Let's put a second parenthesis over there, curly parenthesis, curly bracket. This is one part. Minus, then if we do the same thing, this is again the velocity, right? Vi.
Yeah.
Yeah.
So vi dot ddt of delta ri by delta qk, and then we have variation qk. Okay.
Yeah.
Okay. One thing, we call it cancellation of dot. My claim is delta ri by delta qk is equals to, not definition, it's equals to delta ri dot by delta qk dot.
Yeah.
I claim.
We can prove it actually.
We can prove it. How?
Actually by using the chain rule.
Yes. So take this delta qk dot of. So we do not know if these two things are correct. So let's start with this part. Delta ri dot over delta qk dot. So delta qk, and now ri dot is just velocity, and that like we can expand that as sum over j delta Ri by delta Qj dot plus delta Ri by delta T, right? And then look, this thing is a function of coordinate only, delta Ri over delta Qj. So it's a purely derivative of Qj. It's not a function of velocity. So that's by UV rule, we get delta Ri by delta Qj unaffected, then delta Qj dot by delta Qk dot, and summed over.
Which is dr delta.
No, it's Kronecker delta.
Sorry.
This
Sorry.
Qk dot, Qj dot over Qk dot. So it is basically delta xj over delta xk, which is Kronecker delta jk, right? And again, you have a sum over j. So applying this sum, actually, let's do that later. And for the rest, you have again like delta delta t of this thing, right? Like switch to one thing.
Basically,
that thing is zero. This part is zero, right?
Yeah.
This part is zero. It's a purely function of coordinate. So now we are left with delta R I, but delta Q K. So which we claimed. So basically, you can add a dot over here and over here. You can think like this, these two dots actually cancelling out. So that's why we call it cancellation of dots. So we have this term, delta Ri over delta Qk term, where here delta Ri over delta Qk, right? We can add two dots over there. So if we do that, sum over k, sum over I, mi, and then ddt of vi dot delta Ri dot over delta Qk dot. And what is delta Ri dot? What is Ri dot? What is Ri dot?
Vi.
It is Vi.
Vi.
What is nothing but Vi? So we can replace by this thing. It has started to be nice already. And on the other side, we can do again, but we do in the opposite way, I believe. Oh, no. We actually do this thing. So Vi dot and expand this thing into partial derivative and partial derivative switch, and then recollect those partial derivative. Basically, what it gives you, like time derivative and this partial derivative with respect to Q are switchable. So basically, you are left with delta delta Qk Ri dot. And what is Ri dot? Is velocity. So we can write it like this, Vi. Finally, we got the result we actually wanted. So now we know that total kinetic energy of the system, T, is half m sum over, actually this, for each of the particle half mi vi square, half m v square. So I can write it like this, vi dot vi, and then sum over I. Okay.
Yeah.
So what is delta T over delta Qk, for example? So that is nothing but sum over I half mi, then use product rule. So one is you'll get two terms, like those are same actually. So Vi dot delta Vi over delta Qk. This is what you'll get. So this half and 2 cancel out, and you're left with this part. So basically sum over I mi vi dot delta vi over delta qk. This is what you have.
Yeah.
Why do we have that term? We have this term where
Yeah. Second term
this is
and
the second one.
second term.
This is the second
Second.
term. So if you take this in summation inside here, then sum over I mi vi dot delta qk on vi. So this is what we have. So we can write the second term as, so sum over k, we will write something here. Second term is negative delta T, the total kinetic energy of the system, over delta qk. Also do the same thing for kinetic energy, but take derivative with respect to q dot again. So if you do that, delta T over delta q k dot, what's that? This is nothing but sum over I half mi multiplied by 2 vi dot delta vi by delta qk dot. So this again becomes sum over I mi vi dot delta vi by delta qk dot. Why do we have that term? So take this sum sign inside of that ddt, sum over mi inside of the ddt. So take ddt of something, because mi is a constant, so we can take, and the rest is nothing but delta t by delta qk dot. So we are left with these two things, and these are looking nice. So yes, finally we got the result we wanted actually. So sum over k ddt of delta t by delta qk dot minus delta t by delta qk, and then variation of qk. So now substitute this thing in instead of that ma. This is sum over I mi ai, right? This is that term mi ai dot ri. So now substitute this part. We are almost done actually. So where we are substituting in that D'Alembert's equation principle. So where here. So we had our sum over fi dot delta ri that we expressed. So sum over I fi delta ri, this part could be written as what we got, this thing, sum over j qj delta qj, right? Hello, the first. So this first part can be written as sum over k qk variation of qk, like that. Then we have our that sum over I mai dot delta ri, and what did we get? That we got sum over k ddt of delta t by delta delta qk dot minus delta t by delta qk. That's what we got, right?
Yeah.
So this thing goes to 0. So we can factor out that whole variation qk and take like this sum over k and then whole thing big qk minus ddt of delta t over delta qk dot plus delta t over delta qk. like that. And then variation qk. So
Yeah.
now this whole sum has to be 0, and each variation of coordinate is totally arbitrary. You can fix one and vary the other.
Independent.
So each of them must have a coefficient equal to 0, otherwise it won't hold, right?
Yeah. Linearly independent. Basically.
Yes, those variations are linearly independent. So that's why we can write qk minus ddt of delta t over delta qk dot plus delta t over delta qk equals to 0. So this is again another formulation of Newton's law, right? So
Yeah.
you just take the kinetic energy of the system and take certain derivative and substitute, and you just need to know the specific like generalized force for the system. That's true as well.
Yeah.
So we can we simplify it a little bit further? Answer is yes. So if we have a system for which the force is derivable from the potential, that means force Fi can be written as gradient Vi dot dr, like that. If we have that kind of system, so this is total force F equals to this. Then qk can be written as partial derivatives, right? Like del qk, we can express that thing as derivative of potential delta V over delta qk, like that. Can you see it, or I just need to prove it?
Yeah. It's just a directional derivative.
Yeah, it's the directional derivative. Actually, I meant to write this. Actually, I didn't mean to write this. I meant to write this. So delta delta W, that's what we defined, sum over J, sum over I, Fi dot variation delta Ri, right? And that what we could write like this: sum over K BQK dot variation QK, right?
Yeah.
So if Fi is a derivable from a potential Vi, then we can write like this: sum over I gradient of Vi, sorry, gradient I of V. That means this I index means the coordinate of a specific particle we are picking. Take derivative with respect to that coordinate on the potential. So that dot this thing. By chain rule, this thing like grad V dot dr is nothing but this sum over I delta V over delta xi plus delta V over delta yi plus delta V over delta z variation delta z, right? You can write like that. Just evaluating the dot product.
Yeah.
Also we want our like variation of qk out of this thing. So just explicitly express this thing. So that would give you delta V over delta xi over delta qk variation qk, and so on. Like do the same thing for each of the terms.
Yeah.
So by factoring out variation qk, you'll have delta Vi over delta xi over delta qk, and obviously you'll have the sum over k as well, plus delta vi by delta yi by delta qk plus delta, oh sorry, not vi, it's just v, right? I mistakenly wrote that. Zi by delta qk, and then at the last variation qk. So do you see what is delta vi by delta xi by delta qk plus this thing? What is this thing?
You
Just the
So yes, delta v by delta qk, if you expand that by chain rule, that is basically delta v over delta xi by delta qk plus
yeah.
delta v by delta yi by delta qk, and obviously we have a sum over I. So with this sum up to this part, this is nothing but delta v by delta qk, right? So we can write sum over k delta v by delta qk variation qk, and substitute that. Instead of like we initially had like k qk variation qk like that. So we have now an expression for qk, which is delta v over delta small qk by comparing. So as we have an expression for qk, which is delta v over delta qk small qk, then we can actually reduce down our equation a little bit and write delta v. Oh wait, I made a mistake in the definition of the potential. Usually we write force as negative derivative of the potential, not the positive one.
Yeah.
So I should write negative grad v. So there should be a minus sign, and a minus sign over there, and a minus sign over there. And now we substitute like qk equals to negative delta v by delta small qk. That's the usual definition actually. You could define in the other way, but usual definition is with a negative sign. So minus delta v by delta small qk minus ddt delta t by delta qk dot plus delta t by delta qk equals to 0. So this is our reduced new equation, like when the system is derivable, like the force, all the forces in the system are derivable from single potential. So
Yeah.
potential, if potential is a function of coordinate, so if you take derivative of that, like with respect to the velocity delta v by delta q dot qk dot, this is 0, right?
Yeah.
Potential is not a function of velocity, so we can add a 0 term on the both side.
Yeah.
So yes, so we write ddt delta big V by delta qk dot, which is nothing but 0. This part is 0. Then minus delta V by delta qk minus ddt delta L by delta t by, oh, I wrote correctly but said wrong. Then plus delta t by delta qk. Now potential and kinetic, those energies are looking in the equal footing, like those appear similarly in the equation. So what we can conclude from here,
We can take t minus v.
we can get t minus v to be a single object, and we call it L, the Lagrangian.
Yeah.
And with this definition, if you collect this term and that term, that two term, that gives you delta L by delta qk, right?
Yeah.
And the other term with a factoring out of minus, then ddt of delta L by delta qk dot. That thing goes to 0. So this is our new equation of mechanics. Instead of Newton's law, we have this equation is called Lagrange's equation. Actually, the previous one, like q equals to something, that this equation also Lagrange's equation. This one is also Lagrange's equation, but it's not the convenient one. This is the useful one actually. Lagrange's equation. So just determine the kinetic energy and potential energy of the system, and then take the separation between those two, and then like substitute in this Lagrange's equation, and you'll find the equation of motion. So we'll take a break, but I should accept some questions as well. I'm really sorry. Again, I screwed up something, and that's why it took a while to derive this small thing. Derivation is usually simple, but I actually made it complicated.
So this equation is just the second law of Newton, right?
Sorry, yeah, it's equivalent to Newton's second law, but there is a catch. When you are applying it to a non-conservative system, it's not directly applicable in this original form. So that's a catch. But even non-conservative system, you can directly apply your Newton's law.
So for non-conservative force, if they can be expressed as the potential of velocity, then we can
Not always. Not all systems can be expressed in terms of some velocity dependent potential. So that's a problem as well. So in general, you could have a system that has forces that cannot be derived from a even velocity dependent potential. So in that case, we also have a formulation that's quite new, like in 2013, like quite recently, 2013, in Physical Review Letters, there appeared a paper. That actually derives this Lagrange's equation for non-conservative systems as well. And it seems like in non-conservative systems, like the time reversal symmetry, that actually plays the actual role. Like by time reversal symmetry, we mean like, consider your particle is moving in a drag force system. So it doesn't matter which direction your velocity is, whatever the direction, you always lose energy.
Yeah.
So it's not a reversible system. So this kind of irreversible systems, they have problematic properties. So, and it's quite recent people discovered it in 2013.
Could you please share the journal link in our Google chat?
I can share that. Yeah.
Thank you.
I have a question actually. I was wondering if we could do these similar treatments for real displacements. If we could, then why the virtuals?
Why do we need to deal with those constraint forces anyway? Like, those are not doing anything. So if something is not doing anything, it's better to leave those, right?
As talking about the virtual displacements, if I talk about the real displacements, the virtual work by the constant force are also zero, isn't it?
No. If you're talking about real displacement, let's consider for the not real displacement. I mean, okay, I confused actually. So what do you mean by real displacement? That you need to define.
That the path actually, particle follow that path.
Okay. So before solving the motion, do you know which path the particle is following? Consider this one. So you know that for this cylindrical system, so your marble actually follows this way.
Helical path.
Probably this way. So you actually want to work with only that track, right?
Yeah.
So
but I don't know.
To know that trajectory, first you need to solve the equation of motion with the appropriate boundary condition.
Yeah.
So at the beginning, when you're constructing the equation of motion itself, you have to be pretty general. It could be this
But
direction.
what about the freezing of time? Why do we just define virtual displacement such a so that we have to freeze time?
Okay. Okay, that's another issue actually. So that's the issue of like taking variation and time derivative like being compatible or switchable. That's a different thing. Main goal is to like ignore the effect of those like I mean those constraint forces. That's the main goal. So problem is, if you had your ordinary displacement, say like for a pendulum, if you had your ordinary displacement, arbitrary ordinary displacement, so your dr could take in this direction, but when you are considering your dr to be in arbitrary direction, you are also considering like effect of what's the work done by those constraint forces as well. Yeah, one of those constraint forces has positive work, one of those will have negative work, and they will eventually cancel out. That's true, but you are actually considering those and calculating those. You have no other way to like ignore at the very beginning. But with this kind of displacement like delta r, that is already consistent with the constraint, that you have the scope.
But if we just consider the possible displacements that are allowed by the constraints, but no freezing of time, then also the virtual work is 0, because I am the virtual force is also perpendicular to the possible displacements, if I say that, if I call that.
Say that again, I didn't get it.
I don't want to consider the freezing of time.
I did not consider at all. I did not consider freezing of time.
Variation of time was 0 in that treatment.
But should we consider that we are freezing the time when we are defining the virtual displacement?
Oh, so you think like
Yeah.
when I did delta r over delta t, this thing, I said this thing to be 0. That doesn't mean that my r is not dependent on t.
Yeah.
So this is also another issue. This is basically t is a parameter. You do not vary t. You can take a change in t. You can take this thing, but you cannot take this thing. This is not even defined in this context.
Actually, I have a confusion from those reading those books I have read. They say that when I'm having a virtual displacement, it doesn't take any time interval to do that. So
yes.
So why do we consider that? If we consider that a possible displacement that can take time to happen.
Okay. Yeah, that's a problem. So when you apply Newton's law, say F equals to ma, this is actually frozen in time. So we are applying this thing at a particular t equals to t naught, right?
Yeah.
It's a local thing. So to find a motion, obviously you do the same thing for each of the time, like t1 equals to something, t2 equals to something. You do. That's why we have a general F equal mm equation that actually for all time it's satisfied, right? But it's still a local thing that each of the time that happens. So we want our mechanics to be like that.
I have a question. For example, I have a constrained surface, and if I consider a virtual displacement on that surface, then I will consider that at that time, all the forces are as it is, and I won't consider that time will pass on and then I will calculate the virtual displacement. Is it something like that?
Yes,
Virtual
yes,
work.
yes.
But
Yes.
in actual displacement,
You're doing everything at a particular time, t equals to t naught. So that's everything is local here.
yeah.
So
Okay.
say you're defining some work that is actually happening over some time. What's the problem with that? So problem is your delta W, it started at a time, say t equals to t naught, and ended at a time like t equals to t naught plus delta t.
Okay, yeah.
So now question is, when this work done is happening, like, is it local anymore? No, this thing actually happens over an interval. So it depends on the history now, which way that particle followed and so on. So we want it to be like just at a particular time. It has to be local, and all Newton's law and all law we talk about in physics usually local.
Yeah.
Now I get it.
So, if I did not get what is virtual displacement, I'm actually confused.
Sorry?
What is virtual displacement? And what's the difference between normal displacement and the virtual displacement?
Okay, so when we talk about ordinary displacement, so you have to be a little bit careful about talking about like what you mean by your displacement. So there are two usual meaning. Number one, you actually have a motion and you're seeing that particle is following something, and at a specific time you just take two consecutive snapshot and you see that your particle moved from one point to another.
Yes.
Oops. So on this surface, like your consecutive shot, your particle moved from there. So this is one way we call it as a displacement.
Yeah.
This is obviously a real one.
Yes.
But that is no good in constructing equation of motion. To construct equation of motion, you need everything to be general, because particle with same differential equation, with same equation of motion, particle might follow in another path if you just consider just different initial data.
Yeah. For example, velocity.
Yes, for example, initial velocity or initial acceleration.
Yeah.
So in that context, that's also the usual way we call it displacement. And in that sense, that displacement is also not the particle is taking.
It might take.
Like your pendulum. Your pendulum is following this trajectory. So if you take two consecutive snapshots, probably you will find at this point and that point. You'll say that, okay, this is my displacement. This is actually the real one. No doubt about it. Now, when we talk about like setting up the equation of motion, we could say that particle, say at t time it was somewhere, and after some time it went to somewhere else. And we consider just two arbitrary points in space, like this and this. And this is so much arbitrary that not even this displacement is not even consistent with your actual trajectory that particle can take.
So we can say it's the virtual displacement is the displacement that the particle might take.
Yes, I would say can take. Virtual displacement is the trajectory that is an infinitesimal displacement that a particle actually can take, because that is consistent with your applied constraint.
Then we apply the initial condition. For example, initial velocity.